Okay, welcome back to another video lecture for Math 13-16, Plane Trigonometry. And this is the first in a series of video lectures for this course. In this particular section, we'll be covering 1.1, the properties of angles, and discussing some of the definitions with angles as well as what constitutes a positive and negative angle measurement. So, if we recall back to college algebra, our complex numbers, multiplication by I has the effect of rotating 90 degrees counterclockwise. So that if you have the number 1 and you multiply it by I, it ends up on the vertical axis, the I axis, which we could say is like the Y axis, and that would be positive 90 degrees. And if we continue multiplying by I, it will have the effect of next sending a value on the I axis to -1, and then multiply by I again, it will send it to the negative I position on the Y axis, and then multiplying by I a fourth time will send this to the 1 position, completing a circle. So it's important to note that in plane trigonometry, all of these concepts are sort of based on the rotational aspect of complex numbers. And so that counterclockwise rotation is like the reference point that we name all of our angles from. So if we give a positive angle measurement, for example, positive 45 degrees, it means that we have rotated off of the x-axis 45 degrees in the counterclockwise direction. 90 degrees would be rotating counterclockwise 90 degrees, and so on. This also gives us a way to rationalize negative angle measurements, because negative angle measurements will simply be a rotation in the opposite direction. And you can kind of think about this like if you take 1 and multiply by negative I, then our complex numbers from college algebra will send it to the negative I position, which is on the negative Y side of the graph. So multiplying again, it will send us to -1. Multiplying again, it will send us to positive I. Multiplying again will send us back to 1, thus completing the circle. So there are two definitions with angles that we want to be familiar with before we get into the meat of the course. And that is the definition of an angle complement and an angle supplement. The reason for this is that a lot of things can be defined in terms of complementary and supplementary angles, where complementary angles are any two angles that add up to make 90 degrees, and supplementary angles are any two angles that add up to make 180 degrees. So we have a definition here. If we take theta and then theta complement, add them together, that'll be 90 degrees. And so theta plus theta supplement will be 180 degrees. In other words, if we want to find the supplement of any angle, we simply take that angle from 180. Similarly, if we want to find the complement of any angle, we simply take that angle measurement from 90 degrees, and that will give us its complement. So some examples using complementary and supplementary angles. If we create a angle by dividing up a quadrant on the xy coordinate grid with a ray like this, then we know that the quadrantal angles are all right angles. In other words, the two angles formed, this one and this one, must be complementary. So here I have 2x is one of the angle measurements and 3x is the other angle measurement, and it wants me to find the measures of both of the angles. I could even go like a step further and like name these. This could be A, B, C, and D. So this wants us to find what the measure of angle A, B, D is equal to, as well as the measure of angle D, B, C. What is this angle and what is this angle? Well, because we are dealing with a quadrantal angle that's been divided up somehow by this ray, we know that the definition of the complement is sufficient here. So if I take the algebraic expression that represents the measure of angle ABD, that would be 2x plus its complement, 3x, must equal to 90 degrees. So that is 5x equal to 90 degrees. Now, it's important to note that we can only do this when we know that what we are dealing with is complementary. And the reason that I know this is because the angle ABC is marked as a right angle here. In other words, I know that this particular ray and this particular ray are quadrantal angles to each other. So x will be 18. And then, of course, we can find the individual measures of ABD by multiplying x, which is 18 by 2. That'll give us 36. And then we can multiply 18 by 3 to find the other one, which gives us 54. Consequently, it's also worth noting that once I know this angle measurement is 36, I can just say, well, what is 90 minus 36? And that should equal to 54 by our definition. In example 2, we have a straight line that has a ray fixed at a point on the straight line coming off of it. And then I have defined the angles by their measurement 2x and 7x. And I could go a step further again and label these things if I wanted to. So the problem will be asking us what is the measure of angle ABD and what is the measure of angle DBC again. Now notice that because ABC is a straight line, it is a straight angle, we know that the two divisions of this hemispherical or two quadrants worth of graph here, we know that these two angles must be supplementary to each other. In other words, 7x plus 2x must equal to 180 by our definition. So 7x plus 2x must equal to 180. That gives us 9x is equal to 180, or x is 20. So then I can find what the individual measures of ABD and DBC are by taking our x, which is 20, and multiplying by 7, and then taking our x, which is 20, and multiplying by 2. So DBC is 40, and ABD will be 140, or in other words, it is 180 minus 40, which will give us 140. Now, the study of trigonometry became particularly useful with navigation. So one of the things that we pick up from the study of spherical trigonometry, which is one of the ways in which ancient ships were able to know what their position on the globe was from the location of the stars, one of the things we pick up here is a special way of denoting decimals that works off of modular arithmetic. So we have the so-called degrees, minutes, and seconds notations that give us a way to measure fairly precisely decimals out to the nearest thousandth. And it turns out that in most practical applications, trig values with 3 significant figures are sufficient values. So we pick this up from the study of navigation, and it's one of the reasons why we have to learn how to use this type of thing. So there are several calculations within degrees, minutes, and seconds that we would like to look at. But first, some quick definitions with those concepts. So a degree, we know that the sum of 360 degrees is a full circle. So secondly, we know that 1 degree is equal to 60 minutes, and of course 1 minute is equal to 60 seconds, which is also to say that 1 degree is 3,600 seconds. Now these are actually pretty simple conversion factors like we would use in, say, a physics or a chemistry class if we had something that was done with time. You can think of degrees like they are the hours, and minutes like they are the minutes on a clock, and seconds like they are the seconds on a clock, because 1 hour is 3,600 seconds or 60 minutes. Now, when we do calculations with these things, what it is important to notice is that because the conversion factor for both minutes and minutes to seconds is 60, we are working what we call modulo 60. In other words, every time we have a number that exceeds 60, we simply subtract 60 from it, and we add one more to the place value that is higher than that. So, for example, if I have 6 degrees, 12 minutes, and 72 seconds, this is equal to writing 6 degrees, 13 minutes, and 12 seconds. That's because in modulo 60 arithmetic, any number that is greater than 60 can be reduced by 60. We get 12 by taking 72 minus 60 and adding one more to the place value higher than it. So this allows us to do some fairly simple calculations using degree, minutes, and seconds. For example, we can have 28 degrees, 35 minutes, which is usually written this way, plus 63 degrees, 52 minutes. And if I want to very quickly get the answer to this, what I do is I just add the degrees to the degrees and the minutes to the minutes. You can think about these like they're similar units, so they can be added. So 28 plus 63 will give us 91 degrees, and then 35 plus 52 will give us 87 minutes. But it's considered improper to leave anything in the minutes or seconds position which is greater than 60, because those units we work modulo 60. So remember, as we did right here, I can work with a number bigger than 60 by subtracting 60 from it, which will give me 27 minutes, and adding 1 to the next place value higher. So this addition will give us 92 degrees 27 minutes when we apply the modulus of 60 to it. Now in reverse, we can do a similar thing. If I take 180 degrees minus 117 degrees and 29 minutes, we can perform subtraction using the same sort of borrowing algorithm that we used to use in, say, the second or third grade. You know, borrow one from the tens place. That gives us 10 ones to work with. It's just every time that we borrow from a position higher, it doesn't give us 10 of something, it gives us 60 of something, because we are working modulo 60. So in order to do this subtraction, this is like 180 and 0 minutes. So to subtract 0 minutes and 29 minutes, 29 from 0, we must borrow from the degrees. So this is actually like performing a calculation. 179 degrees, 60 minutes, minus 117 degrees, 29 minutes. And then, of course, the same thing as before. These are all like similar units, degrees to degrees, minutes to minutes, so we can subtract them. 179 minus 117 will give us 62 degrees, and 60 minutes, oops, put a minus symbol there, 60 minutes minus 29 minutes will give us 31 minutes. And it's in this way that we can perform additions and subtractions using degrees and minutes and even seconds. It would just be like adding one more place value. And again, remember, we are working modulo 60. Now, sometimes we are asked to convert, and some of you may ultimately be more comfortable doing this. We are asked to convert degrees, minutes, and seconds into a decimal notation. And that's just something that we're used to dealing with from like geometry. We get a decimal on our degree symbol, and then we just kind of leave it like that because high school geometry doesn't teach this sort of thing. And really, I'm actually not even entirely sure if college geometry teaches degrees, minutes, and seconds. I think it's really the first time that you see it when you get to plane trigonometry. So the conversion is pretty simple if we remember what the conversion factors are for each of the minutes and seconds units. Now you can choose a number of different ways to do this. Really what I like to do is to use the t-tables for stoichiometry the way that we would in like a chemistry or physics class. This is my personal favorite way to do it, but I do want to just show you the flat conversion here first. If you wanted to take something to degrees only, but it has a decimal representation, we can take the degree number plus, and then the minute number divided by 60, because there are 60 minutes in a degree, and plus the second number divided by 3,600, because there are 3,600 seconds in a degree. So if you were to type this all into the calculator, what you will get is a decimal representation for this number here. So that happens to be 105 plus a fraction that represents 1/3 plus, and then 32 on 3,600. This will end up being, as a decimal, 105.3422. Okay. If you wanted to do this with the t-tables, you could simply take the minutes, and notice that 1 degree is 60 minutes, and then we could also take the seconds, 32 seconds, and notice that there are 3,600 seconds in 1 degree. We could get these two decimal numbers, add them together, that will be 0.3422, and then add that to 105, and that will give us our decimal representation. Now, also, we might want to go backwards from a decimal representation to a degree, minutes, seconds representation. And one of the reasons for this is that in degrees, minutes, seconds, we have this nice modulo 60 arithmetic that we can do with it that gives us a way to add and subtract them without having to worry about a lot of the problems that we run into with decimals. Now this should be noted that this really only works super well when the length of the decimal attached to the degree measurement that we have is only 3 or 4. And that's because when they get much higher than that, then that usually means that the seconds unit will actually have a decimal on it. And frankly, that's not any better than just dealing with a decimal representation in the first place. But you have to remember this was a product of the times that it came out of, so it has a few advantages, but it also has a few disadvantages. If you wanted to go backwards, now there's a very nice feature in the TI calculator that we can use for this that makes going backwards actually kind of trivial. We might want to convert something like 85 point and then 263 degrees into degrees, minutes, seconds. Now, if you were on your calculator, you can type in 85.263. Then if we press the second key and the apps button, which is the angle menu, you'll notice that option 4 says DMS with a little arrow next to it. After you type the number in and you choose this option, it will automatically convert this into a degree, minutes, seconds representation. Now, if you don't like using the calculator for this, then it really actually is not all that bad to do the rest of it by hand. If we wanted to do this by hand, what we're going to do is the degree number will just be the degree number in the final answer. So what we really want to work with is 0.263. So in degrees, we know there are 60 minutes. So if I multiply 0.263 by 60, it will give me 15.78. Well, notice that the 15 in this number is the same as the 15 in the final answer. So I can just, again, cover up the 15 and take the decimal off, which is 0.78, and multiply by 3600, as you will see from this t-table. Oh, sorry, 60 from this table, because we're already in seconds there. So 1 minute is worth 60 seconds. So since we're already in minutes, we just multiply by 60 again, and that gives us, of course, 46.8 seconds, 46.8 seconds. And you see that our answer that we get manually is the same as the answer that we get from the calculator. Now, a couple of other minor things that we want to talk about here is what do we mean by quadrantal angles? So the quadrantal angles are just the angles of rotation that will correspond directly to the x-axis, the y-axis, the negative x-axis, and the negative y-axis. So those numbers are 0, 90, 180, 270, and 360, noticing that 0 and 360 are the same thing. So a lot of what we do in trigonometry is modulo 360 because we're dealing with rotations. So if I were to give you an angle like 540, we could just start subtracting 360 off of that angle until we ended up with something that was less than 360 but greater than 0. And that would be what we call an angle in standard position, is that it is between 0 inclusive and 360 not inclusive, because if it is 360, then it is the same thing as writing down a 0. So what we can do is take rather large angle measurements that would be difficult to work with. For example, something rather large, maybe in the thousands, like 1106 degrees, or something that's like negative that we don't want to deal with if at all possible. For example, negative 150 degrees, or something that's a combination of both. It's very, very big and negative. And what the standard position allows us to do is notice that all of these angles are just like spinning around the origin several times, so they will end up in a place that you could measure with a smaller number. The only difference is that 1106 degrees means that we have spun around several times before ending up in the final position. So if I were going to stand in front of the camera looking this way and I want to turn to face here, I could make a very short 45-degree turn, or I could spin around several times and also end up looking at 45 degrees from the camera. So you can see how a larger angle measurement can be reduced to something smaller. What this translates into is the effect that subtracting 360 degrees has on something is nothing except that it makes the number smaller and easier to work with. So the same thing is true for adding. The effect that adding 360 has to a degree measurement is nothing except it makes the number more positive and potentially puts it into standard position, which is of course easier to work with. So what that means is you can freely add or subtract 360 to any angle and you will get something that is ending in the same position as it. Another word for that is you will get an angle which is coterminal with the pre-existing angle. And coterminal angles have the same trigonometric properties as their bigger counterparts, which is why we like to search for things in standard position, which are angles between 0 and 360 degrees. So with 1106, we can just start subtracting 360. And the first time I get 746, do it again, we get 386, and do it a final time, we get 26. So this particular 1106 is the same thing as 26 degrees. Now with negative 150, we could add 360 to it once, and it will be the same thing as 220. degrees, which is an angle in standard position. Now with negative 603, we can add 360, and the result will still be negative. It's negative 243, but doing it a second time will give us an angle in standard position, which is 117 degrees. Okay. Now, any time we have angles that are in degree minutes seconds, it might be useful to try to convert them into a decimal, and you will be asked to do several operations with numbers in degree minutes seconds. And although it's kind of a long way around, a suggestion: if you don't like the degree minutes seconds units, you can memorize the conversion that takes them into a decimal form, and then just add them there, and when the Pearson asks you to put your responses in degree minutes seconds format, you can just use the calculator key, second apps option number 4 on the answer to put it into degree minutes seconds format. Now the other things that are worth mentioning here is that at this point in 1316 plane trigonometry, if you are on a TI calculator, you should be using the degree mode, and you should be set to real answer value. So on the mode key in the calculator, you want the calculator in normal mode, you want the rounding to be set to float, you want to be in the degree mode, not the radian mode. You should be in function mode. It'll say connected or dot. You should always have it say connected. It'll say sequential or simultaneous. You put sequential. And then where you have the option from college algebra of having complex number answers a plus bi, you do want to be in real number answers at this time. And if you have those things set up, then you understand everything for 1.1.